Can you still see my screen?
Yep, again.
Yes, we can see.
Yeah.
Okay, great. Thank you. So this is the introduction to embedded systems. In the textbook and many places in this lectures, we use cyber physical systems. We'll see the difference, and they do not differ that much. I think it's just the terminology. We'll talk about these as we move along the slides. We'll talk about embedded systems and cyber physical systems, and these contents are based on chapter 1 in the textbook. And at the end of this lecture, I will talk a little bit more about how we prepare for the labs. I want to acknowledge the authors of the book. They provide many of the slides. Okay, so focus on cyber physical systems. As you see on the slide, those are the applications or environment where you can see a lot of the systems that sense any of these surrounding environment and make decisions on either control certain actuators or motors or devices. And for example, the automotive example, the cars, if you think that you are having thousands or millions of components in your cars that are controlled by electronic systems, and there are a lot of sensors in your cars, especially the nicer cars. You may have a temperature sensor, you may have your lane departure sensor. Those are the things that you can expect in cars, and you expect that you have electronics systems to record these sensors, provide you the information, and that you make decisions of how you should drive the car, or even the car itself to manipulate the car's movement. Other situations, for example, manufacturing, as you can see, this two robotic arms trying to do something with the body of the new car. You can expect this kind of machines, mechanics, and electronic systems in a modern car factory. Other applications, avionics, airplanes. It has a very complex control and sensing system. Also in biomedical fields, military, or even the modern buildings, you can expect to see a lot of these components or systems that belong to either physical aspect or cyber aspect. We'll say this cyber plus physical is because you have the physical systems way before the cyber, right? You can have a paper airplane flying without any electronics control. But when you get to more complex, more sophisticated systems, oftentimes it's not physical itself, it's not cyber itself, it's a combination of both. And the idea is to use cyber systems to interact with physical environments, physical dynamics. So there's a computation perspective and dynamics perspective. And the dynamics could be continuous dynamics, or could be discrete dynamics. So like the robotic arm in this picture, it moves continuously. But for buildings, the dynamics could be, flip the switch on or off, 2 states. And in these different application domains, there are different requirements on the security, safety of these systems, and which required us to design the system by considering different requirements, different capabilities. There are contradictions in the design of such systems. There's often the adaptability versus repeatability. So we would like a system to be able to repeat. For example, we want to build this car using the same procedure. So these robotic arms will perform the same procedures, sequences for, car 1, car 2, and car 100. But still, we want the system to be able to change to building a new car. So it's a sedan versus a SUV, and we want to change the robotic arms sequence differently based on what kind of cars we want to build. Also, for connected devices to the network, we are facing the contradiction between the high connectivity and the security and privacy. So if you connect a device to the internet, you have the risk of exposing it to security threats. But if you keep it isolated, then you lose the opportunity of scaling this further and have remote control capabilities. Other metrics or requirements are performance versus low energy or low power. You want to have high performance computing systems. At the same time, you would like to have your laptop to run, a day or even longer without having to have a recharge. Asynchronous versus coordination, cooperation. You want the system to be able to respond to asynchronous events such as interrupts, but also when you have multiple of these, you want them to work in a collaborative way. For example, if you have a group of UAVs or unmanned area vehicles or drones, then you want a group of them to be able to communicate and perform, to accomplish a task together. Scalability and reliability and predictability, those are all important, but sometimes you have to sacrifice maybe predictability or reliability in order to achieve scalability. It's hard to get every aspects taken care of. And laws and regulations and technical possibilities, those are not always on the same line. You can do this technically, but from the legal perspective, can you or should you do that? So that's always a question of balance. Economies of scale versus locality. People, some of you have heard cloud computing, maybe, fog computing. Those are all, trying to scale, but when you put things in the cloud, you have less control over the data sharing contents. On the other hand, if you keep the data locally, then you will have challenges of sharing this data and reach to a larger scale. Open versus proprietary, that's obvious, contradictory. And algorithms versus dynamics. So this is really talking about the physics part of the picture versus the cyber part of the picture. It might be easy to perform a dynamics in a physical world, but it may be a complex algorithm if you try to do that. For example, if you move your arm, just emulate this movement of the robotic arm, you can do that. Not on the cars, but you can move your arm very flexibly. But if you want to control a robotic arm, just to mimic the movement of your arm, and that's not an easy thing. You have to consider, the actuators at different, part of the arm, and have them move at different speed and different angles. So from algorithms point of view, that's a very complex process. So the point is that if you want to have these innovations and important applications in these different fields, the design of such cyber-physical system requires new engineering methods and models to address these contradictions. Okay, here we have a nice picture. Do you know this E pluribus unum? This is actually, I didn't know until very recently. This is actually the motto of the CEO of United States. And if you look at the coins that you have with you, you'll find such words. This is in Latin. It means out of many, one. They had this in the early days in the United States, just because the United States is made of multiple states. Now you have one union, so that's one out of these many. What we want to say here is that you probably heard a lot of these different terminologies: Internet of Things, Industry 4.0, trillion sensors, machine to machine, the fog, all these terminologies. And they actually are the foundations of this cyber-physical system. A cyber-physical system may not have everything, but it's fair to say that every piece of these technologies, the advancement of technologies, has made the cyber-physical system possible. So talking about the very popular term Internet of Things, there were a lot of hypes around Internet of Things, good and bad. The idea of Internet of Things is to use internet technology to connect physical devices or things. You may have billions, trillions of things that are being built and connected. It follows a curve that experienced by many different other technologies. So it goes from the innovation as a start, and then it ramps up people's expectations, and then when it gets to application stage, it may go down a little bit because people see a lot of challenges, and then eventually overcame the challenges, and then as a result, that technology will become ubiquitous. So this kind of curve is expected for many of these technologies that are marked here. For example, quantum computing, that's very hot. I will not be surprised that in 5 years, quantum computing will be one of the courses in the curriculum here, maybe as a required course, maybe as a tech elective. But the other terminologies or technologies, for example, data science, you've heard that a lot. Let's see, smart robots, connected home or smart home, big data, all these. So Internet of Things is also going through this kind of hype. There's peak of inflated expectations, and eventually it will go through this curve by overcoming the challenges and becoming a ubiquitous technology. So that's what we see what's going to happen for Internet of Things. But coming back to the cyber physical system, is IoT the same as cyber physical system? We say that IoT is the use of internet technology for cyber physical system. We've seen a lot of this networking technology used in cyber physical system, even early days in 2008, as you see in the picture shown here. Bosch, this company has this printing press. It's a cyber physical factory. The reason we say that is all these machines, these print machines, they are connected in a way that using Ethernet and TCP/IP. So those are the network protocols that you probably heard. And using these networking technologies, they can provide high precision clock synchronization for these individual machines on an isolated LAN. So, strictly speaking, this isolated LAN is not connected to the internet. But, if we look into this system, it has networking technology locally to connect these individual machines. IoT term includes the solution of internet technology in a problem statement connected things. But the term cyber physical system does not really emphasize or require this internet technology. What we mean by that is cyber physical system here, we emphasize the interaction between the cyber system and the physical systems. It may connect it to internet, it may not connect to the internet. For example, you have a car. So the car is a typical cyber physical systems because you control all the either using steering wheel or using your the dashboard to control the functions of your car, moving forward or backward, or accelerate or deaccelerate, turn left or turn right. This is the typical cyber physical system. But does it have to be connected to internet? Well, in the future, maybe every car will be connected to internet, but now they are not connected to internet in most of the cases. So what we want to say here is that IoT does not equal to cyber physical systems. Whereas in our class, we will talk about mainly on the cyber physical systems, specifically how we model the physical system and how we model the cyber part of it, and how we design the system to implement the design goals and ways to analyze the design. We have this design, and it may or may not use internet technology. So it may or may not be a IoT, but still it's a cyber physical system. Now, the book used cyber physical system exclusively for describing these systems that integrate or interact tightly with electronics and physical procedures. You can think about these are the embedded systems that we're talking about. These systems are, especially the control part is typically small, and their functionalities are typically dedicated for example, the robotic arm, it's built for robotic arm. It's different from these laptops and HPC servers, which can be used for general purpose computing. Where in our case, the systems we're going to study and design are small, dedicated functions, have stringent design requirements. Okay, so here is an example. It's the flying pastor example. Flying pastor is a machine that's being used for high-speed, high-volume printing. If you're interested, you can click this link to go look at the explanation of the flying pastors. Essentially, you will show you a video after this one, but what you are seeing here is really a machinery in a printing house. It's totally different from your personal printers, which takes those letter size or A4 size stack of paper sheets. The printing house that we're looking at here is using these large machines, and the paper that they want to print on is not supplied as individual sheets. Instead, they are supplied using these large rolls, very thick, large rolls you will see. And the rolls will be, unrolled, and the paper will be supplied through a series of steps. Add a roller dancer to move, the pages. Sorry, not the page, the paper through this drive roller and eventually feed into the printers. But these rolls may be used up. Then you have to replace the paper. Now, we're talking about big printing house. So they are expecting these machines to print books or magazines continuously. So any interruption about this machine will be costly. So the goal here is to supply an endless row of papers to these printing machines, or at least try to supply a new row before the old row is going to be completed. And that's the machinery we're going to be seeing in the next video, where these system is trying to have very precise positioning and also turning these rows at a specific speed so that the new row of paper can be spliced or stitched to the existing row and continuously feeding these big printing machines. So let me show you the, sorry, I don't know if you can hear. This is, in the factory, so it's kind of noisy. But this is the new row they want to feed in. So this is the old row. Now the old row, is spliced with the new row, which then continuously supply these, long sheets of paper into these printing machines. This video is actually available on this website. I think what we show here is just a shorter version of it. You can see the complete one on this website. So as you can see, this is a big machine. Obviously, this is a very complex physics process, physical dynamics. We have large rolls rotating, and also we need to have these big, flying arms to rotate the other row and trying to splice these two rows, and then at the right moment perform this cut so this new row can continue supplying the paper sheets. As you can expect, the control of the system is very delicate. You don't have to have a laptop to do this, but you have to be very precise in terms of moving these two rolls and perform the right, press the right amount of force and cut the sheets at the right moment so they can be spliced together and coming continuously from the new roll. Okay, I just want to check here. Can you still hear me? All right.
Yes.
Yes.
Yeah.
Thank you.
Yes.
All right. Before I show you this next one, just want to warn you that it's a little bit disturbing because we're showing some problems here. This is a typical off-ramp of a highway and a typical day, but something happened. So the 18-wheeler suddenly made a unexpected turn towards the center of the highway and just fly over that the fence and then cause a chain of actions and of course accidents, and I'll be surprised if there's no people injured or even dead. But this is a very challenging problem for cyber-physical systems in that how would you design a system to prevent such horrible things from happening? And there are a lot of things we can do to at least reduce such risk. That's a good example. Well, that's an example that can show us the importance of a properly designed cyber-physical system, and also shows the consequences if the design is not successful or not reliable. All right, this is a fun picture to show. So we have an elephant, and of course we have quite a few people trying to examine what is an elephant. Depends on where the person sits or stands or looking at, they have totally different response. And because they don't see the big picture, they only feel a part of it and different parts of it. So it's challenging to work in this multidisciplinary area as this CPS design. So in the CPS design, you may see that this is a small computer if you only look at the computation part of this design. Or you can say, oh, this is a networking issue if you are only concerned about how this device connects to internet. You may think about, oh, this is a robot. Well, you are right in some regard, but what's in a robot and what's the purpose of it? And also you may think about this as an advanced manufacturing. Well, yes, that's a possible application domain, but what entails the requirements and what will be the cost and other constraints? That's something we have to put into the design process. Okay, again, using car as example, those automotive CPS has far greater impact than probably many other fields, because cars that with people every day, it's important to have safer transportation. And also from the environment perspective, we would like to reduce emissions. I think these several weeks I saw a lot of commercials from Amazon who is trying to do this environmental protection initiative, trying to supply the battery-powered vehicles for delivering Amazon packages. Also, for smart transportation, we would like to have cars to be able to interact with each other, and also we would like to have cars to interact with the roads. So in a smart transportation system, we will have to think about how we can sense the environment, not only the car itself, but also the surrounding environment and the other cars. And when we move into battery, vehicles, battery-powered vehicles, we would have to talk about energy efficiency, so that we can, reduce the impact to the environment, and also alleviate the impact to climate change. And when you have human in cars, if you look this car as a robot, then this human robot or human machine collaboration or interaction is also important aspects when we design such a futuristic automotive autonomous vehicle and for the smart and safer transportation. The other example is also from cars. So as people designing cars, and especially designing high efficiency engines, we're talking about still the fuel engines, it's important to control the air-fuel ratio so that we can reach the optimal state for the purpose of reducing emissions. The engine has this catalytic converters that can reduce CH4, carbon dioxide, and oxide emissions. And the conversion efficiency can reach optimal at this stoichiometric value. So there's a narrow window for the air-fuel ratio in order to achieve this optimal efficiency level. Now, how do we achieve that then? So in a gas engine setting, we would have something like this. We have this engine here, and we have the fuel injectors will inject fuel into the engine so that they can burn and perform these chemical reactions, and then move the pistons of the engine. So in order to achieve this perfect or optimal air-fuel ratio, we need to have these sensors at different places. So in this diagram, this way, this is the air incoming path, or the intake manifold. And on the other hand, this is the exhaust manifold. So this is how where the smoke will be emitted to the environment. So we will ideally have these sensors at these two places, which will measure the air flow, also measure the air-fuel ratio from the exhaust. And these sensors will provide vital information for the control system to determine how the fuel injectors should be open or closed. And so that we can achieve these optimal air-fuel ratio. So in this system, we have sensors, we have actuators, which are the things we control, and also we have the cyber-physical system, the computing part, which is not illustrated in this diagram. So this is a good example that shows that we will have these very important components in a typical cyber-physical system: sensing, control, and actuation. Many of these cyber-physical systems have to have this in order to have a system to interact with the environment, with the machinery for this particular application. Well, the software here is going to be important as part of the embedded system for the computation. All right, so this is a diagram that illustrates some of the disruptive technologies, as pointed out in about 7 years ago by McKinsey Global Institute. So they developed research to find out, okay, what are the far impact technologies that will provide profound benefits for society. For example, mobile internet. So that's where you can access a browser or emails on your cell phone. And here, Internet of Things, cloud, advanced robotics, advanced oil and gas, and 3D printing, advanced materials, all these. And even this list is given 7 years ago. You can see these are still very hot terminologies, or still people are trying very hard to achieve, to advance in these technologies. Out of this list, we can see that many of them have major CPS components. The things that are not highlighted here are the automation of knowledge work, cloud technology, advanced materials, and next generation genomics. Those are probably more on the high performance computation side, neural networks, machine learning. But the other ones that are highlighted here, they all have major CPS components with them. For example, mobile internet, your cell phones have a lot of sensors, and they are connected to internet, and they have those computing resources to perform these controls and then to provide information to you. And advanced robotics, of course, as we see in the very first diagram slide, in that robotic arm, we have a lot of the capabilities of doing sensing, do flexible controlling, and also intelligence to automate the tasks. The potential economic potential also is significant. For the Internet of Things, we expect a 3,000% increase in connected machine-to-machine devices. We have about 1 trillion things that are connected to the internet. The operating cost of the affected industry will be 36 trillion. I won't repeat these numbers on the slide, but as you can see, all these areas or technologies that involve CPS have huge economic potential and impact. That is good news for us as a computer engineering or electrical engineering or other majors, engineering majors. We have a lot of a room to explore, to investigate, and to study and to advance, to improve these technologies and achieve the better performance metrics and better goals. The next 2 slides are about several companies and how they invest in CPS design and systems. Google acquired a company called Nest about 6 years ago. At that time, Nest is a company with just one product. That's the learning thermostat. Thermostat has been with us for a long time, probably maybe 100 years, a wild guess. But until Nest, people have been using thermostat in a very rudimentary way. It can measure the temperature, of course, but it does really not much more than that. Nest was the company that connect these thermostats by re-engineering it, by redesigning it into a cyber physical system. So it still measures the temperature, but these temperature data can be sent to the cloud because this Nest sensor have this networking capability. And that's a game changer. Because once you have these thermostats and millions or billions of these data samples collected, you can do a lot of learning and analysis on these data to make smart decisions on whether to control the AC or furnace or heating system, to reduce energy consumption, to reduce your cost. I think that's the reason that Google see this as a very significant change to a traditional physical device to a intelligent cyber physical system. Similarly, robotic car from Google has a lot of sensors built onto the car. Also, it has the computation capability to generate a 3D map of its environment, and then takes the generated map and combine them into high resolution maps of the world. The other example is this solar-powered drone. This is a artistic rendering of Titan's Solara 50, which in theory can stay aloft for years. And this company has been acquired by Facebook, I think, by Google. The purpose of this drone is to provide uninterrupted network connectivity to remote areas using this autonomous solar-powered drone, which can fly for weeks and months. Okay, Tesla has done many groundbreaking things recently. What's the space mission? Have you seen that the whole story in the summer?
Yes.
Yeah. What's the name of the vehicle?
Dragon.
Dragon. Yes.
Yeah.
Dragon is one of the things that Tesla team have done magnificent job by sending astronauts to the International Space Station using a commercial vehicle. In the past, only NASA did that, and now Tesla is changing that, the whole picture, to make it more cost effective, because the vehicle Dragon can be reused. So what we see here is a different thing done by Tesla. This is the gigafactory. This is the picture. Well, it's not the actual picture. It's the artistic rendering of the battery factory being constructed in Nevada. I think the project started a couple of years ago. Tesla had this huge plan of, have this gigafactory, and several important things and interesting things about this factory. This is a factory that will manufacture batteries and the battery engine pack for Tesla cars. And this is a huge factory, and it will consume a lot of power when it runs. The good news is that the power to drive to run this factory is all coming from itself or nearby wind turbines. So on the top, on the roof, all these solar panels, they can generate a lot of power. And the nearby wind farms, so those are the wind turbines that will generate power in megawatts to drive this factory. Not surprisingly, there will be a lot of cyber-physical systems. Even each of these turbines is a complex cyber-physical system, because the wind turbine have to turn, and you have to have sensors to sense the speed, detect any damages, and also to start or shut down the generator if necessary, and for maintenance and for other purposes, and also to maintain speed and to schedule power delivery. So all these things have to be done in the electronic system with tight interaction with the physical systems. Okay, Apple car, iCar is still a mystery. There are a lot of rumors Apple been designing some kind of iCar in-house, but we still, don't hear any official news. Maybe we'll hear that soon. But this is one of the autonomous car practices or plans in the world. I think all the new car manufacturers are talking some kind of electric autonomous car, that will be available in the near future. So if we look into this cyber world, we see the in the core, we call it infrastructure core, we have a lot of the big machines, big routers, server farms, data centers, cloud environment. And further away, we see this mobile access devices, laptops, smartphones, Game Boy consoles, music players, all these. And many of these are connected to the internet. And then even at larger scale, in terms of quantity and the area that is deployed, you can see these sensor swarms, or billions of sensors for temperature, for stress, for motion, for chemical processes, for visual sensing. So all these are layered structures of this emerging IT world. All right, so I spent a lot of time motivating, about cyber physical systems and why they're important, what they are, and any design requirements, examples. So back to this course, we would like to use this course to introduce a principled scientific approach to design and implement embedded systems. we can take let's say, Arduino development kit. We can go ahead, putting things together, make something that can function. But in order to really understand the engineering design process and have this principled scientific approach, we need to go beyond just hacking with embedded systems. Hacking can be fun, but if things go wrong, you have to spend a lot of time to ask yourself why this is not working, and how we should, resolve this problem. And because it can be very painful when things go wrong, so we need to really step back and then think at higher level to understand how we should design a system. In fact, we should start by using some models to capture or to estimate what kind of design we will have. So we'll focus on both model-based system design. But on the other hand, when we get hands-on and we have to present this deliverable, we cannot avoid the hacking part of it. We will have to do this embedded system hardware and software design. So that's why the other piece of this course is really the design aspect. In order to introduce the principled scientific approach to designing and implementing embedded systems, we will go through this model analysis verification steps. We will try to capture the essence of the system, the goals, using some models, and then we will analyze it and verify at different stages. We will go through a journey of these hands-on experiments, especially using these lab assignments. We will look into the system architecture of the designs. We will try to understand the actual tools we use to design hardware and software, and the methodologies for debug and optimization. We'll focus on both model-based system design and embedded system implementation. But in this process, we will try to apply theoretical results and methods in the real applications. So you can expect that in the lectures, we will cover many of these important concepts in modeling these cyber-physical systems, the methods to analyze them with some examples. Also in the lectures, and especially in the lab assignments, we will use these concrete lab assignments to give you a chance to practice this method. Let's talk about modeling, design, and analysis, three integral part of this designing process. Modeling is the process of gaining a deeper understanding of the system through imitation. So we may not have to drill down to individual processors or memory chips or I/O components we'll have to put together, we'll have to buy. In the modeling phase, we don't really care about that. We just want to use the models to express what a system does or should do. So you outline the functionalities, and oftentimes you also specify the performance metrics. For example, if you design a digital camera, you want to say that I want to have a feature on this digital camera that is taking continuous pictures. So you can say, I want, enable the users to do this if the user press the button and hold the button, the shutter button, until the button is released. So this is a good example of what kind of functionality you want to have in this design. And also for this particular function or feature, you want to design certain performance metrics. For example, I want to achieve continuous taking pictures 20 pictures per second versus maybe 5 pictures per second. Those are important design goals metrics, which can be part of the modeling. When we get to the design phase, the design itself is a structured creation of artifacts. So at the design phase, we will need to specify how a system does what it does. This includes both the hardware and software perspective. We need to, at this stage, pick the right processors, right memory components, right interconnection buses, peripherals, power supply unit. And also we need to connect them if they are hardware, and also design and implement software algorithms and deploy onto these hardware platforms. So the design phase specifies how a system does what it does. The third phase is the analysis. Analysis is the process of gaining deeper understanding of the system through dissection. It specifies why a system does what it does. So once you have the design, you want to check if the design meets your design goals or system specs. Analysis is such a step because we can analyze the performance of the actual design when your team finished the design. We can then find out whether the shutter speed, if you hold the button continuously, can the digital camera produce 20 pictures per second at that speed. So analysis can tell you whether your design works, meets the requirement or not. If not, and then we have to go back. If you see the picture on the right side in this slide, you will see there are a lot of arrows pointing from one box to another box. This is really to say that these parts are overlapped, and we need to go through this design process iteratively. Maybe we need to change the model. Maybe we need to change the design, and then do the re-evaluation. So it's a very complex, sometimes time-consuming process before you can end up with a design that meets the performance requirements, cost requirements, and all the other constraints. The textbook that we're going to use in this course is from professors at UC Berkeley. It's written for this course, strive to identify and introduce the durable intellectual ideas of embedded systems. The book itself emphasizes the three pieces that we just talked about: modeling, design, and analysis of cyber-physical systems. You can download the book for free from this website. Check what time is it. Okay, I think I'm gonna keep going without taking a break. So we might be able to end the class a little bit early. Feel free if you want to step away for couple of minutes and come back if you want to take a short break, but I'll just keep going here. All right, so this is a motivating example of a cyber-physical system. In the picture here, we see a drone. Actually, it's a Quadrotor aircraft. This particular aircraft is called StarMac. It was an experimental system drone testing platform built at Stanford. It was from a research project. There are many challenges of building this kind of a drone or a flying cyber-physical system. First, how do we control the flight? So as you can see here, this is a Quadrotor, so which means it has 4 rotors at each corner, and you can control the speed of each rotor, which produce different thrust pushing downwards. You can adjust the thrust force by changing the speed of these rotors to perform different movement. For example, moving forward, backward, or even flip over. So the control of such flight is very complex itself. Also, the other challenge is the weight. It carries a battery, in addition to the control circuit. It may carry other load. So how do you design the system so that the amount of thrust produced by the rotors can carry these payload at a certain speed? And because it has weight, so it can be dangerous. So the third challenge will be, how we should design it so that this Quadrotor aircraft can interact with the environment and maybe also with the human safely and effectively. So those are, some challenges that you can imagine when designing such a cyber-physical system. In this cyber-physical system, as we can see in the next few slides, that there are a lot of components. But talking about all these challenges, the right side here on the slide shows the list of these topics that will be covered at different chapters in this textbook. For example, flight dynamics, mode of operations, transition between modes, sensors, actuators, processors, memory systems, interfacing, concurrent software, and analysis, etc. In our course this semester, we will not be able to cover every single chapter, but I'll show you each week that which chapter we will cover, and hopefully you can read the contents in that particular chapter. Okay, so this is a diagram I was talking about. This shows the internals of the Quadrotor StarMac. We don't have to go into very detail, but you can see here there are different colored boxes. There's 3 colors. The green color boxes, those are all sensors. You can recognize some of them, GPS, camera. LiDAR is a very precise distance sensing method using radar, short-range radar. AMU, this is the one we're actually going to use in the second lab. In addition to these sensors, we have those yellow boxes. These are actually processors or computational units. And we have 3 different kinds. If you're curious about it, this RoboSticks is actually based on Mega chip. This is a microcontroller that we use. Well, it's the same kind of microcontroller we use in our labs, but it's not exact the same model. This type of microcontrollers can perform real-time control operations. So the low-level flight control is done by using this microcontroller. This other two are more at higher level because both of them run operating systems. And this one is used for supervision of this whole system and also performing GPS localization and a communication using Wi-Fi. And this one is using for estimation and control, running those robotic control algorithms, for example, reinforcement learning type of algorithms. So those are the yellow boxes. Then we have these purple boxes. These are Wi-Fi interfaces. So this is the networking fabric that we'll also talk about in later courses. Using Wi-Fi and other network technologies, we will be able to control the system from a remote point. Okay, so the theme of this course is to think critically and design systematically. Any course that purports to teach you how to design embedded system is misleading you. This is not my word. This is the word from the author of the book. I kind of agree. I think the point is that you cannot just teach embedded system design by handing you over a bunch of microprocessors and other components and wires and let you connect and program it. That's only one part of it. It's because the technology will change. The processor that you use today may not be available the next year. And the components that you use in today's class, in the next year, you may have a new version of it. So it's important to teach you how things are done today, and also why that's not good enough. You will learn the theoretical part of this course and to understand the methodologies, the fundamentals behind these different tools and the processors available today. And you will not be surprised by the changes that are coming, and sure, they will come.